Guys, today we are going to talk about the properties of integral. So I think let's see what we have done before. Here. So we have discussed fundamental theorem of calculus, and in this course we are talking about continuous functions, right? So on closed interval, right? So and we define, so we know the definition of the antiderivative of f, right? And then we talked about the fundamental theory of calculus, which is this one. When you differentiate, so f is continuous, then you can define a function like this. So you can show that this uppercase f is continuous, and if you differentiate this function uppercase f, you get the same function. You can obtain the same function lowercase f on this interval here, right? And also according to this definition of antiderivative, we can say that if this function also an antiderivative of f, right? And the second, under the second theorem, if f is an antiderivative of f, notice that if f is an antiderivative of lowercase f, uppercase f is an antiderivative of f on this closed interval AB, the integral of f over AB interval is same with these difference, uppercase f of b minus uppercase f of a, right? And we have discussed the linearity of integral, right? If you have a constant inside the integral, you can pull it out from the integral, right? Like this. Both are the same, right? Both are the same. And addition, the integral of addition of two functions is with the sum of integrals, right? And we have done these kind of, we can find the derivative of this very easily. I think we have done a prac class for this on this, right? So now we are talking about the properties of the integral, right? Suppose f is a continuous function on closed interval AB, so f is non-negative on this interval, right? Then the integral of f over AB is also non-negative. So this is very clear. Why? So f is non-negative over this interval. So that means if you consider any partition of AB interval, PB a partition of AB interval, so x naught the same with a, x sub 1 up to x sub n minus 1, x n is the last point of the partition, which is same with b. And this, you know, this one is greater than, this one is less than, no, this one is less than, this value, less than or equal to that, less than or equal to that, no, less than, right? So this is the partition in each subinterval. So if you consider this subinterval x sub r minus 1, x sub r, this interval, you know that because f is continuous, you can find maximum and minimum. So maximum of m represents capital M sub R on this interval, right? The maximum of f, function f, on this interval represents uppercase M sub R, and minimum of f on this interval represents lowercase m sub r, right? So because f is non-negative on this closed interval, therefore these values also non-negative. Therefore, so we know that lowercase of f corresponding to P partition is less than or equal to integral of f over a b interval, and less than or equal to upper sum of function f corresponding to b, right? This inequality is true for any partition of a b interval, right? Because of this, and in each sub-interval, this one is true. Therefore, these are non-negative. Therefore, what happened to this integral? That integral also non-negative, right? It's also non-negative. So if you look at this theorem, this property here, you can this implies this trivially, right? This one is true, right? What is the other one? Let's see the other property. So if the function is non-negative over this interval, on this interval, and there exists element in this interval such that the function value at that point is positive, then this integral is positive. If you have a point on the interval such that the function value at that point is positive, this integral is the integral of f over ab is positive all the time. I think you can prove this one. I think I don't focus on this part of proving this one because we haven't learned some basic stuff, right? Or you can say this is your function and this is your point C, right? This is your point C. Where is that? Yeah, this is your point C, and you can find a delta gap. So this gap is delta, right? This gap is delta. So you can find a delta such that the function is positive, remains positive. So you can find a delta such that the function remains positive, right? The function is positive because f is continuous, right? F is continuous. Let's say, wait a minute. So this is the thing, because f is continuous. So, and if you have a point in this interval such that the function at that point is positive, therefore you can find a positive delta gap around this point such that on this interval the function is positive because this function is continuous. That's why we can find this delta here, right? So, right? So what is the gap of this, what is the width of this interval? Width is 2 delta, and 2 delta f of x is also positive in this interval here, right? So therefore you can say that you can prove that this integral also positive if you consider any part. Yeah, you can show that. I'm not going to show that part, right? Because we are using these things to solve problems, right? So let's look at the next problem. There's an here. This is a problem here. Suppose f and g are continuous functions on closed interval ab. If f of x is greater than or equal to g of x for each x on this interval, then the integral of f over ab is bigger than the integral of g over ab. Why is that? If you consider f minus g, because f and g are continuous, then f minus g, this is a function. This function also continuous on this interval. You can apply this theorem here, this property here, because this is true for each x in AB interval, then this one is non-negative for each x in AB interval, right? Then you can apply this property, right? Then the integral of these two, integral of f minus g over AB interval is non-negative. You can split this integral into two integrals, because this one is same with, because integral operator is linear, it's a linear operator, right? This one is same with integral of f over ab minus integral of g over integral of g over ab, right? There you can take this integral to other side, right? Then you get this property here, pretty easy. And the second one is, if f is non-negative for each x in this in closed interval ab, and there x is a point in this interval such that f, the function value f is bigger than g at that point, so then this integral is greater than this integral of g or ab interval, right? This one is clear, right? And the other one is, f is a continuous function on ab, then this one is true. You can show this one. I think let's see, we can do this theorem very easily. I will do a video on this, right, next time, right? So far we have discussed properties of integrals, right? If f is continuous and f is non-negative on this interval, then the integral of f over that interval is non-negative. And if f is non-negative and there x is a point in the interval such that the function value at that point is positive, then integral is positive, right? Like that, right? Okay, let's in my next video I'm going to discuss about mean value theorem for integrals. So, right, Alright, see you next time.